In today's lesson, we're going to look at binding energy. We will be looking at first the mass difference during important reactions like fusion and fission. By mass difference, we mean what is the difference in mass before and after in each of these two reactions. We'll also be introducing Einstein's mass energy equation, which you're probably familiar with, E = mc squared. And we'll be using it to calculate energy released during these fusion and fission reactions. And then lastly, we'll be using some units of abbreviation. EVs, which you have come across before, electron volts, mega evolts, and we'll be looking at a new unit called the unified mass unit, which simplifies the mass, which is formally in kilograms. Okay, so that's what we're doing today. Let's introduce this atomic mass unit U first. 1 U is equivalent to 1.6605 times 10 to the minus 27 kilograms. This allows us to manipulate numbers much more easily because we're dealing with numbers that are so tiny. This enables an abbreviation and it makes the maths a little bit easier to handle. The value 1.6605 times 10 to the minus 27 comes from a simplification. It's defined as 1/12 of the rest mass of an unbound atom of carbon-12. The rest mass is 12 grams. So if you can work out how many nucleons there are in 12 grams of carbon-12, which we'll look at a little bit later on, then you will find that approximately the mass of one nucleon is equal to this U. So 1 U is approximately the mass of one nucleon, although we'll look at the exact values in a moment. Right, so the first exercise we're going to do is we're going to consider a helium nucleus. Helium has 2 protons and 2 neutrons. That's 4 nucleons in total. I'm going to show you some information about the mass of neutrons and protons, and what I want you to do is to use the individual masses to work out the total mass of a helium nucleus. And here we have the mass of a proton, and we're going to use the fancy new unified mass units U. The mass of a proton is equal to 1.007276 U's. The mass of a neutron is equivalent to 1.008665 U, and the mass of an electron is 0.005486 U's, but we're not going to bother with the electron right now. So, using this information, build a helium nucleus, calculate what the mass of a helium nucleus is from its constituent nucleons. You should have worked out that two protons and 2 neutrons give you a mass of 4.031852 unified mass units. But in reality, the mass of a helium nucleus is much less than that. It's 4.001506 unified mass units. There is a mass difference, a missing mass. Einstein postulated that this missing mass is actually converted into pure energy. When you put those nucleons together, something happens, which then releases energy. And he postulated that this energy was used to bind the nucleus together. And that's why this energy is called the binding energy, delta E. It holds the nucleus together. The mass difference then between the individual masses of the nucleons and the mass of the final nucleus is called the mass defect, delta M. Einstein came up with an equation which allows the calculation of the amount of binding energy in a nucleus. And that equation, which, as I stated before, you're probably familiar with, is delta E, binding energy, equals mass difference, or mass defect, times the speed of light squared. The speed of light being 3 times 10 to the 8 meters per second. So now you can calculate the binding energy for any nucleus. So let's have a go at nitrogen-14. Calculate the binding energy when we have 7 protons and 7 neutrons. Here we have the value of the individual masses together, and here is the mass of a nucleus. So calculate now the energy in joules. Okay, so your answer in joules is 1.6 times 10 to the minus 11 joules. How do we do this in evolts now? Well, you want to abbreviate, you want to make your answer smaller. So you divide your answer by 1.6 times 10 to the minus 19. That will give you your answer in evolts. And then you divide your answer by a million, or 1 times 10 to the 6, and that will give you your answer in mega evolts. So try that now. So hopefully you've got an answer of 101 mega evolts. There is an abbreviation that you can use, which is on the data booklet. As it's not always convenient to do this large, heavy step calculation, finding the mass difference, and then using U equals mc squared, etc., mass is quoted in atomic mass units, not kilograms, and energy is often quoted in mega evolts. So you can use a mass energy conversion as follows. 1 U is equal to a difference in mass of 1.66 times 10 to the minus 27, as you already know. And then this conversion is on the data booklet. 931 mega evolts is equivalent to 1 unified mass unit. So you can use this conversion directly. And as I said already, this is actually on the data booklet. So have a quick check. We did this right at the beginning. Work out the binding energy in mega evolts of a helium-4 nucleus. So this is what you did at the beginning of this lecture. And using that quick conversion, that 1U is equal to 931, you should have calculated a value of 28.2 mega evolts. Okay, now that's it for today, more or less. Let's go back to our objectives. You calculated the mass difference that occurs during fusion and fission. Well, we focused on fusion, and fission we will have a look at a little bit later on. You have used Einstein's mass energy equation, E equals mc squared, to look at binding energy and mass difference or mass defect. And you've also expressed energy in joules, evolts, mega evolts, kilograms, and a unified mass unit of U. So that's it for now.